Welcome! In this exercise, we will study the differentiability of the case-defined function f of x. This function is equal to the cube root of x plus 3 when x is less or equal to minus 2. It is equal to 1 minus e to minus x squared when x is greater than minus 2 and lower or equal than 0. It is equal to x times sine of x when x is greater than 0 and less or equal to pi over 2. Finally, it is equal to the absolute value of pi minus x when x is greater than pi over 2. Let's recall two useful results that will be used in the following. If the function f of x is differentiable at the point x0 of its domain, then f of x is continuous at x0. Otherwise said, continuity is a necessary condition for differentiability. The second result is about the limit of the derivative function. Let f of x be a continuous function at x0, and if we assume that there exists a neighborhood I of x0 so that f of x is differentiable in I, with the sole exception of x0, moreover, if we assume that the limits of the derivative function, the left limit L1 and the right limit L2, exist, then if these two limits are equal, we can infer that the function f of x is indeed differentiable in x0 and that the value of the derivative in x0 equals the value of the two limits. In other words, the existence and equality of the left and right limits of the derivative at a point x0 are necessary and sufficient conditions for differentiability at x0. Given these two results, in practice we will first identify the points of discontinuity of the function. Those points will be for sure points where the function cannot be differentiated, since continuity is a necessary condition for differentiation. Then we will check the differentiability of the case-defined function in each subinterval. Finally, we will identify the points at the subinterval boundaries where the left and right limits of the first derivative of the function are different. Those points will be for sure points of non-differentiability of the function, since by this second condition, the existence and equality of left and right limits for the first derivative is a necessary and sufficient condition for differentiability. Before proceeding with this plan, however, let's first expand the absolute value. The absolute value of pi minus x is a case-defined function itself. In fact, the absolute value of pi minus x is equal to pi minus x when pi minus x is greater or equal to 0. This means when x is less or equal to pi. Moreover, it is equal to x minus pi when pi minus x is negative. This means when pi is less than x. By combining these two expressions, we obtain that the function f of x is equal to the cube root of x plus 3 when x is less or equal to minus 2. It is equal to 1 minus e to the minus x squared when x is between 2 and 0. It is equal to x times sine of x when x is between 0 and pi over 2. And it is equal to pi minus x when x is less or equal than pi, while it is equal to x minus pi when pi is less than x. Before proceeding further, let's notice that the function f of x equals a continuous function in each subinterval. Then, let's start by identifying the points of discontinuity for f of x. Since f of x is continuous in each subinterval, the only points of discontinuity will reside at the boundaries of each subinterval. Then, it is sufficient to study the left and right limit of f of x at each subinterval boundary. The first boundary point is x equal to minus 2. When x is less than minus 2, then the function f of x is equal to the cube root of x plus 3. This means that the limit as x approaches minus 2 from the left of f of x is the limit as x approaches minus 2 of the cube root of x plus 3, and this is equal to the cube root of x plus 3 evaluated in x equal to minus 2. This since the cube root of x plus 3 is a continuous function. This equals the cube root of minus 2 plus 3, and this is 1. When x is greater than minus 2, the function f of x will be equal to 1 minus e to the minus x squared. This means that the limit as x approaches minus 2 from the right of f of x is equal to the limit as x approaches minus 2 of 1 minus e to the minus x squared. This, since this function is continuous, is again the function itself evaluated in minus 2. This means 1 minus e to the minus x squared evaluated in minus 2, and this equals 1 minus e to the minus 4. The second boundary point is x equal to 0. When x is less than 0, the function f of x will be equal to 1 minus e to the minus x squared. This means that the limit as x approaches 0 from the left of f of x will be equal to the limit as x approaches 0 of 1 minus e to the minus x squared. This function is continuous. This will be equal to 1 minus the exponential evaluated in 0, which is 1. So this means 0. When x is greater than 0, the function f of x will be equal to x times sine of x. This means that the limit as x approaches 0 from the right of f of x is equal to the limit as x approaches 0 of x times sine of x, which is equal to the function x sine x evaluated in 0. This is, of course, 0. The third boundary point is x equal to pi over 2. When x is less than pi over 2, the function f of x will be equal to x times sine x. This means that the limit as x approaches pi over 2 from the left of f of x will be equal to the limit as x approaches pi over 2 of x sine x. By using again the continuity, this is nothing else than x sine x evaluated in pi over 2, and this equals pi over 2, since sine x in pi over 2 equals 1, that multiplies x evaluated in pi over 2, this means pi over 2. When x is greater than pi over 2, the function f of x will be equal to pi minus x. This means that the limit as x approaches pi over 2 from the right of f of x equals the limit as x approaches pi over 2 from the right of pi minus x, and this equals pi minus pi over 2, which is pi over 2. The fourth boundary point is x equal to pi. When x is less than pi, the function f of x will be equal to pi minus x. This means that the limit as x approaches pi from the left of f of x will be equal to pi minus pi, which is 0. Moreover, when x is greater than pi, the function f of x will be equal to x minus pi. Again, the limit as x approaches pi from the right of f of x equals pi minus pi, 0. Let's summarize what we have obtained. The left and right limits in 0 are the same, as well as the left and right limits in pi and in pi over 2. On the contrary, the left and right limits in minus 2 are different, since the left limit equals 1, while the right limit equals 1 minus e to the minus 4. This means that the minus 2 is a point of discontinuity for the function f of x. Instead, the function f of x is continuous at any other point. Let's switch now to check the differentiability of the function f of x in each subinterval. When x is less than 2, the function f of x will be equal to the cube root of x plus 3, that can also be written as x plus 3 to 1/3. This means that f prime of x, the first derivative, will be equal to 1/3 that multiplies x plus 3 to 1/3 minus 1. This means 1/3 that multiplies x plus 3 to minus 2 over 3. Finally, f prime of x will be equal to 1/3 that multiplies 1 over the cube root of x plus 3 squared. You should notice that the first derivative is defined only when x is different from minus 3. When x is between minus 2 and 0, the function f of x is equal to 1 minus e to the minus x squared. This means that f prime of x, the first derivative, will be equal to the derivative of 1, 0, minus the derivative of e to minus x squared. This means e to minus x squared that multiplies the derivative of minus x squared. This equals to minus e to minus x squared that multiplies minus and minus plus 2x. When x will be between 0 and pi over 2, the function f of x will be equal to x times sine of x. This means that f prime of x will be equal to the derivative of x, 1, that multiplies sine of x, plus the derivative of sine of x, which is cosine of x, that multiplies x. When x is between pi over 2 and pi, the function f of x will be equal to pi minus x. This means that f prime of x will be equal to 0 minus derivative of x, which is 1, minus 1. Finally, when x will be greater than pi, then f of x will be equal to x minus pi. This means that f prime of x will be equal to 1. Here we have summarized what we have just obtained. Now we will identify the points at the subinterval boundaries where the left and right limits of the derivative are different. In this way, we can check the differentiability of f of x at the boundary points. You should notice that it's not necessary to study what happens at x equal to minus 2, since we have already established that the function f of x is discontinuous there, and this means that f prime of x will not be defined as a consequence. We can calculate easily the limits left and right at each boundary point, as we have done for f of x. As you may notice, the limits are obtained by simply evaluating the expressions we have obtained for the first derivative at each boundary point. You should notice that in 0, the first derivative is continuous. In pi over 2 and in pi, the first derivative is discontinuous. Then we can infer that the first derivative will not exist in pi and in pi over 2, while the first derivative of f of x will exist in 0 and will be equal to the value of the true limits, which is 0. Summarizing, the first derivative is not defined in -3. Moreover, is not defined in -2, since there the function is discontinuous. Finally, the first derivative is not defined in pi/2 and in pi. There the function has 2 corner points. This completes the exercise.